in measuring the force on the required to wind up the wheels in the cart, we see that we could exert a 2 Newton force. If we pull the cart back 10 centimeters, the average force is 2 newtons. Now that force isn't really constant. As we pull the cart back and the wheels get tighter, or as the spring in the wheels gets tighter, the force does go up, much like a rubber band. However, it's initially under some tension, so it doesn't go up as fast as we might think. In over 10 centimeters, it's pretty close to constant at 2 newtons. So we have approximately 2 Newton force over 10 centimeters. So we have to do 0.2 joules of work on that cart to wind up the wheels, pulling it back through 10 centimeters. And that amount of energy goes into elastic potential energy. Now let's just think of what would happen if that work went into kinetic energy. We'll say that, actually I'll tell you that the cart turns out to have a weight of about 1 Newton, which means that its mass is approximately 100 grams or 0.1 kilograms, as we'll see in a minute. If 2/10 of a joule becomes kinetic energy, then we're going to have, well, the expression for kinetic energy is 1/2 mv squared, and that's going to be the kinetic energy. Okay? In other words, we allow the car to start from rest and take this 0.2 joules of energy and convert it to kinetic. If that happens, then the velocity the cart attains is going to be easily found by solving this equation. Multiply by 2, divide by n. We get velocity 2ke over m, plugging in our known quantities, the 0.2 joules, the 0.1 kilograms. We end up with a predicted velocity of 2 meters per second. And I'll tell you that when I release that cart, it does not attain a velocity anywhere near 2 meters per second. So, not sure where the excess energy is going, but we're trying to illustrate energy conservation here, or in this case, the difficulty for accounting for all the energy. It's all there somewhere. We're just not sure where it is. If we let the cart run up an incline, we find that the cart will run up an incline and climb about 2 centimeters with this 0.2 joules of energy. Again, we simply pull the cart back, measuring the net force that's used to wind up the wheels, and we get the 0.2 joules of energy when we pull it back through 10 centimeters, when we roll it back 10 centimeters. And if we lift a 100-gram car 2 centimeters, which is essentially what happens on this incline here, when we calculate the force, we take the force times the, to lift the force we're going to need a 1 Newton force. To lift the car we're going to need a 1 Newton force in this direction. And we're going to multiply that 1 Newton force that we need to overcome gravity by the 2 centimeters in the same direction as the force that we have to exert. So we exert a force this way, we measure the distance in this direction. We don't measure the distance along the ramp. Anyhow, if we do that, we get a delta W of 1 Newton through 2 centimeters, a 1 Newton force exerted through 2 centimeters. That's 2 Newton centimeters, or 0.02 joules. Only 1/10 of the energy that we observed it takes to, is required to wind up the wheels. Another way we can look at this situation is we have a force parallel, a parallel component of the weight force down the incline. In order to move the car up the incline, it's going to go through a distance here against this force. So that we have to exert this much force in this direction to climb the incline. If we take that force multiplied by the distance along the incline, we get the same result.